Okay, so as we had promised, today we have no lecture as such. So we have brought some experiment. This is essentially to show hopefully temporal interference, spatial interference, and the effect of polarization in interference. And hopefully, I'm not promising that, it depends on whether we succeed. This is not a lab environment, whether this is shaking and all that. We'll see if we can show you some effect of temporal coherence. Spatial coherence we will not be able to show, but temporal coherence is something we can try to see if we can actually show that to you. Okay, so first of all, let me draw a diagram. So what this is a Mach-Zehnder interferometer. This is, I have a camera, then I can show you one by one, and at the end of the class you can come closer and take a look as well. So Mach-Zehnder interferometer, this we have seen. Beam of light comes in, splits into two, and what we have done is like when you do theory, you don't worry about several issues, but in theory, you will have a laser here and light goes like that, but in the experiment, with a mirror here, there's a mirror here, and then light gets into the beam splitter. Once it is in the beam splitter, then it splits it into two. I'm just trying to draw exactly what this is doing. And then on, let's say, this side, you put a mirror like this. Again, not necessarily theoretically, but to make the light go in a straight line, you need these arrangements experimentally. And here, we do a delay line so that I can introduce time difference T1, T2. And then this is another beam splitter. We are mixing it, and we have a camera here that we can do. Of course, the light comes also this side. So we have an arrangement. There's a mirror, and we can also bring it on to the same camera. So we can look at this or that or both at the same time. And this entire arrangement is on a micrometric stage that can be moved back and forth. So that is the setup. So this is the setup we use for studying temporal coherence or temporal fringes. But here we are using this to actually get you spatial fringes. How do we do that? So although I have drawn just like a single ray, but it is always a beam of light, so it has some width. So this entire thing remains the same. But what is happening here is that although I have drawn that, this is completely overlapping with this, but what you have actually, this is a beam splitter. Sorry. This is a beam split. Then of course the light that comes from this side has some width to it, and then light is coming from this side, and then it has some width. They don't necessarily overlap right with the beam splitter, and hence this is so weak. So we have beam of light which is going like that, and another one which is like this. And since these two wave fronts are coming at some angle, you will see spatial fringes. This is exactly how it happens in Young's-Double-Slit interference, right? Of course, if they completely overlap with each other, exactly collinear, then you can only see the effect of temporal interference or interference due to the difference in time. But here you will have interference due to difference in space as well, or because of the k vector. So obviously different. So showing temporal fringes a little difficult. That's why we'll do something that is easier, and then we will try temporal one. If we succeed, fantastic. If not, at least we have seen something. So this is the whole setup. Now maybe I can walk you through this, and for that I can turn on some light. Maybe all the light. That's too dark. Okay. Maybe one more. Sorry. Yeah. Okay. So what we have now, we don't have anything. As a screensaver. Okay, fine. There was a wooden stick or something as a pointer. Oh. Yeah. So this one, where do we start? Yeah. So this is a laser, and then I think I drew it the other way around. This is the laser, and then this mirror and that mirror, and this goes into my first beam splitter. And after that beam splitter, it comes like this, then goes like that, and then comes to the second beam splitter. From this side, it hits it here, then another mirror. No, I don't think you can see it very clearly. Now you can see, right? There's a 3 mirror, 1, 2, 3. So from this side, it comes there, and then gets into the beam splitter. So these are the two possible ways in which it can come, and then it finally mixes at this beam splitter in this manner, that there are some angle, there's a wavefront, and then they are mixing, superposing with each other at some angle, and then we look at the intensity pattern in this camera. So if you now look at this is already aligned, hopefully it should work. Right. So what you're seeing is, this is the camera screen, this is what we see on the camera just being projected there. So this is a 2-dimensional image, and this one is just a 1-dimensional cut along the center. And so this is the maximum, this is the minimum visibility pattern, and that's the number you're seeing, 97%, 94%. Of course things fluctuate, this table is not very sturdy, oh, even 100%, just so you know. So it's a very high visibility. That says, it says that the field coming this way and that way, they have very good coherence. What coherence? Spatial coherence. But what about temporal coherence? If it's very high visibility spatial fringes, what can you conclude about temporal coherence? Of course, we are talking about the temporal coherence of these two beams, these two possibilities. It's very high spatial coherence, but can we say nothing about temporal coherence, or temporal coherence is very high, or temporal coherence is very low? Or this information just not sufficient? High, why?
Because in spatial way, you can W, example, goes across that, we get a single monochromatic component for spatial fringes. If this is perfect, means is good coherence, means that W is also has high degree of coherence.
W is for the spatial coherence.
That is also related to the temporal plasma.
Okay. Yes. So coherence is coherence. It's just that we have tried separating it just for the ease of understanding. But something interferes only if it satisfies the coherence condition for time, space, polarization, angle, everything. So in order to see interference, all coherence conditions need to be satisfied. Even if you're not satisfying one, you will not see interference. So if you do see very high visibility interference, that means coherence is there everywhere. If you don't see interference, you can't conclude that is coherence is not there in any degree of freedom. That only means at least in 1 degree of freedom, the coherence is not there, and that is enough to get rid of the fringes. So very high visibility, this spatial fringes, this means that of course the field that is coming this way, that way, are mutually very highly spatially coherent, but they are highly temporally coherent as well. Again, you can ask a question at any point. This is that is the main point. This is the interference setup. What is done right now? That of course these are aligned very carefully. That's why this set of 2 mirrors and a set of 3 mirrors here. And although I have drawn exaggerated a little bit with this angle theta, but this angle theta is very small. This angle theta is very small in this one. And now you can see what is interfering here is, let's say, if I exaggerate it even further. So that's a wavefront. If you look at just this wavefront, what do you see? This is flat intensity, right? And that you can check that, let's say, if I block this arm by inserting it here, that fringe is gone. And that is how much intensity is coming from one arm. If I block the other one, again this thing is gone, and that is the intensity that's coming from the other one. And if I open up both, that's when you see the interference pattern. Of course, you could see that my overlap was not really perfect. Overlap of the beam, and then this one, and that's why you see very high contrast fringes only in this range. Right? Here, the visibility is decreasing. So here the visibility is decreasing not because you're losing spatial coherence, but because there's an intensity difference of the field coming from the two arms. So if even the intensity is different, you can lose visibility. But degree of spatial coherence remains high. Well, this you have to believe me on this, that this source has very high spatial coherence. So even when there is a high spatial coherence and then there is a difference in the intensities coming from these two possibilities, the visibility can decrease, although the degree of coherence remains let's say 1. So only when these two proportions are equal, then the degree of coherence equals visibility. So this is what you're seeing, that aspect, very high visibility here and not so high visibility here. That's because the beam coming from two sides are not perfectly overlapping. That's there and that's there. So only in the center you can say the perfect overlap as far as intensity is concerned. This was not intended, but this happened, so that's even better. Okay, now just to show you, well, you're probably convinced that this is a real thing you are seeing and not something recorded. So now what I can do, I can change this beam splitter. So this beam splitter has several controls. These are mirror controls. Well, these are controls to change the angle of the beam splitter. So if I change the angle of that beam splitter here, what I am essentially doing is changing this theta. So if I increase this theta, maybe let's say, let me just exaggerate this a little bit. So yeah, so if just one arm, you get flat intensity. Now if I have the other one coming, then the overlap at this detector plane, this is the angle theta. And you're saying that as a function of this x, we see fringes. This is at a given some particular theta, which again I don't even know what the value is, but at some theta. But now if I increase this theta value, let's say at this point some fringe pattern. If I increase this theta value, that means the wavefront which were like this, now is becoming like this. Will you have more number of fringes in the same area or less?
Yes.
If I increase the angle, you sure? Fringe density. Fringe density will increase or decrease? Can you guess? If you increase the angle, this you can calculate. I mean, we'll surely calculate, but I'm just asking you to guess. So yeah, it will increase, but not the fringe period, but the fringe density. So you'll have more and more fringes in that same area. And if I decrease the angle, then of course the fringe density will decrease, fringe period will actually increase. So now let me do something. Now I actually wouldn't know whether I'm increasing or decreasing it, because this is all relative. So whichever increases, now I can claim that I'm increasing theta. If it decreases, I can claim it is. So let's just try it and see if. So did it increase or decrease? Let's do a little more. So now by doing this, it was not overlapping, but of course I'm increasing this angle, but at the same time this overlap is also decreasing. So in this range, of course the fringe density has increased, but now here you're losing interference because the overlap is. So let me bring it back and go to the other direction. Now you see the fringe density decreases, right, because I'm going the other direction. So as I close in, theta becomes smaller, fringe density becomes smaller, fringe period becomes larger. In the event when theta is 0, what happens? Huh? Constant. What do you mean constant? And then constant equal to what? Well, we can compare it with how much intensity we are sending it through the laser. So will that constant become equal to the intensity we are sending from the laser? Yes, no? Yes? What happens to the conservation here? We send in some intensity. Actually, this is a 5 milliwatt laser, so that's how much light we are sending in. So, do we have all that 5 milliwatt coming out of this output port? No? Then what happens? Right now, let's not combine this. I said in principle. So, I mean, some of it will go this way, and some of it will go that way. And conservation will require that how much energy goes here and there. It has to add up to what was being sent from the laser. Right? That will be the requirement. But again, coming back to this point, once we have theta almost equal to 0, then what happens? Because these were spatial fringes. Well, when theta is equal to 0, there is no effect of space. So you will not see any effect, on X as far as fringe pattern is concerned. But the interference can still take place, and it can take place if you change the time difference. Here, by doing all this, I'm essentially changing things in space. And let's say if I bring theta equal to 0, but I can still change T1 and T2 somehow. That will give me a fringe pattern. But where will that fringe pattern be? In space or in time? That will be in time. Right? So as a difference, T1 minus T2, I should still be able to see interference. This conservation conditions will still be satisfied that whatever I'm getting here plus what I'm getting here, that should equal to what came from the laser. Well, so this is then going into the temporal interference part, which I will do in the end, because once we do temporal, I'm not sure if we can align it back. So even if you don't align, at least we can probably stop here. But that is what I kind of wanted to stress, that what we are seeing right now, this is spatial fringes, and by changing this angle, you can see different fringe period or fringe density. And again, as I pointed out, let's bring it back. Right. As I pointed out, that there's a very high fringe visibility here. Maybe it has shifted a little bit, but very low visibility, right? This is not because there's less spatial coherence. This is because there's difference in intensities coming from the two arms. You can have the visibility go down because of loss of spatial coherence, but for this laser, it is spatially highly coherent, so it won't happen there. But if you have a finite beam size, right? This beam has a size like about 1 millimeter or so, half a millimeter to 1 millimeter. So if the beam has a size of 1 millimeter, what can you conclude anything about spatial coherence, size or area from that? Can the coherence area be larger than beam area or smaller? Must be proportional. Huh? Inversely proportional. The beam size and the coherence area. Why? Huh? There is something inversely proportional. What is inversely proportional usually? The Fourier space. Yeah, so that's the one considered generically. Source area and source. Source.
Area will be the beam area.
Huh?
The source area will be related to the beam area.
No, beam is the source. So here they are the same thing. Beam is the source. Now the question is, if the beam has a size, does that tell you anything about the coherence area that the beam has? Beam has a size, beam has a coherence area. These two are independent things, or these two are connected? These two are independent. So the beam has a size, and it can have any coherence area for that matter. So can this source, which has a finite beam size of 1 millimeter, what is the coherence area of this? You don't know, right? This is almost infinite. So that means if in that beam, for example, let me just block it, and then we see sorry, no, that's not what I meant. I meant this. Well, this is almost a beam. You probably don't say it's circular. There's a elliptical and then things like that. This is an experimental imperfection, but it's almost like a beam. So coherence, beam area means this is my beam, and then whatever is its size, that is my beam size or beam area. But coherence means that if I take the field from this point and take the field from that point, will they interfere? And if they interfere, what will be the visibility? If the visibility is 100%, then I can say this point, field at this point and field at that point perfectly coherent. Now if I take a field from here, some field from here and some field from there, then what happens? I can still get the visibility, although the intensity coming from here and there, not as high, but I can still see some interference. Well, if I do see some interference, then I can say that these 2 points are also coherent. Similarly, you can keep going. Of course, this is what's called a Gaussian beam, which is a homework 2 problem, one of the problems in homework 2. So Gaussian kind of extends up to infinity, right? So although it looks like the beam is up to this one, but there is some intensity that kind of continues. So if you can pick up some field from there, some field from there, and interfere, of course the total overall intensity will be very, very low, but it will still have very high visibility. So if I kind of draw the 3 conditions, in one case, when you are interfering, let's say at this point and that point, so that's number 1. You will see very high visibility in the place. Second case, if you interfere these 2 points, of course it's Gaussian beam, so intensity decreases. This time, I think you'll see something like this. So fringe pattern, fringe visibility, everything is same, just the overall intensity that decreases. Finally, if you take a point from here and there will still be some intensity, and in this case what you will see is still the same pattern visibility, but the overall intensity just decreases. So this is fully coherent spatially, fully coherent spatially, fully coherent spatially. So, oops. Can you make it the screensaver for a so yeah, so still not showing in power.
Scaling needs to change, that's why it looks like elliptical.
Oh, can you make it slightly? Unequal stretching.
Yeah.
Okay, just so you notice, the beam has become circular. So it was the scaling was different. So it was not that it was elliptical. So this is still kind of imperfect, but slightly circular. But that was just the scaling aspect. Thank you. Right. So the beam size or the beam area and the coherence area, these are two independent things. Okay. This beam size, of course, you are able to see, and if we interfere, you will see interference wherever the overlap is perfect. What happened? Okay, so any questions so far?
Now the visibility has increased very much.
Where? No, visibility is still high. As I said, the beams from two different paths, they are not perfectly overlapping. So this decreases visibility. That is because the intensity coming at this point from the two possibilities are unequal. Around center it is equal. Okay? And then see very high visibility. Oh, why is it 46%? Oh, I think, sorry, it has shifted. Did you choose not the map somewhere, no? Oh, I moved the camera. Can you bring it back? Let's see. Otherwise, people are doubting that this is a. Yeah. Yes.
As the fringe density was increasing, the amplitude of the inner intensity was decreasing.
As the
As the fringe density was increasing, there is a change in theta. The amplitude of the intensity gets down. Why that's happening?
as the fringe visibility.
Fringe
Density.
density increases. More up.
Mhm.
The amplitude of the intensity gets down.
Oh, that should not be. I mean, of course, this is not a perfect, so there will be some decrease. You're looking at these numbers, right?
Yes.
But it won't be appreciable, maybe 10-15%, not more than that. So 10-15%, I think that will be there, but not more than that. But so whatever intensity is being sent, it gets divided into half. Half comes out there, half comes out there. And fringe pattern, in a sense, only redistributes the energy. So, but then since there is not perfect overlap of the beam coming in the two arms, there can be some maximum intensity can become lower or higher, but there will be not much difference there. Yeah.
It is just due to the
Yeah, it is. And that can always be worked out. But it will not be that in order of magnitude lower or higher, which is what you will see in this kind of thing. That if you have a Gaussian beam, and if you go, on this side plus minus 3 sigma, then this intensity can be 100 times smaller. This point will be 100 times less intense. But if you interfere these 2 points, the visibility will still be 100%. But of course, the intensity will be 100 times smaller. So the beam size and the coherence area, or beam area, coherence area, these are two independent things and can be controlled independently. And the inverse that you are talking about, that is the beam area or the size of the K distribution. Again, the size in time and the frequency width, coherence time and the spectral width. Those things are usually inversely related for stationary fields. If it's non-stationary, you do not have that inverse relation. Only for the stationary field, coherence time and the width in frequency.
No, in even spatial
Mm-hmm.
coherence,
Mm-hmm.
like the source areas inversely related to the coherence area where it is.
That's the Van-Sittert-Zernike, right? In the Van-Sittert-Zernike also, yeah. So yeah, exactly.
Yeah, and this is the coherence.
So again, if you have incoherent source and that satisfies the stationarity and stuff, then again you have that inverse relations here. Same for angle and L.
We will not have a relationship of that sort for coherent sources.
No,
Yeah.
no. In fact, for coherent source, you can actually find out a relation between beam area and coherence area, because the field is not random. The correlation function is just a product of star and non-star field. Hence, the coherence area of the source and the beam size of the source will be completely related. Okay, any other question here?
Sir,
Yeah.
what is the major of this many reflectors?
What is what?
These reflectors we are using.
Mirror.
Yes.
Yes.
Why are you using so many? We can use less number.
Why I'm wasting so much money? It would be better if you just use one. Oh, by the way, one mirror costs about 5,000 rupees. In fact, it has set up for the one mirror because I have a mirror. But you are insulting me, but I am saying that it is an insult. So this is like a mirror, this one, and this mirror. If you actually come close and see, this shiny piece mirror, and then this is a mount in which this mirror is, and then there's a post which we have connected. So the entire thing is about 15,000, and there are so many of them. So you're right. That why are we wasting? So the reason is theoretically again it is just makes no difference. I can just put a line like this and it goes 90 degrees. But if I want to have a there's a beam coming in, if you want to go at 90 degrees, experimentally doing with one mirror is extremely difficult. Of course, theoretically there will be a solution, but getting to that solution with just one mirror almost impossible. But if you have two mirrors, you can get the solution really easily.
No, I am thinking that is there any effect on the result or making many use of this reflectors or mirrors? Is there any result in the result? It's helping out the intensity or using?
No. Yeah, it does. So if I am not able to align the beam, there will be no interference. So this interferometer that we are seeing, we have very carefully, they are very carefully aligned in the lab, and then we brought it very carefully here. So if it is disturbed, getting it back, it will take some time. But if I have these two mirrors and this 3 mirror here, that getting it back can be within few minutes. But if I give you only one mirror to use here and one mirror to use here, you take a day, and you might get it, you still may not get it.
These are helping with good result.
Yes. No. So with these, I can have a very well-defined way of getting back the fringes. But with just one mirror here, one mirror there, it becomes more of trial and error. You might get it, and most of the time you won't get it. So that's why you use it, so that to get it back in a more structured manner. Right?
So this reduces the error.
No, it's not the error. I mean, even getting the alignment, how do you get it? So it is like that. Getting the alignment part. I mean, if somebody, but not that, there's a pistol has something you can look at and so on. There's two holes, and if you align the hole, and then you know who you're shooting. So I mean, you could shoot like this also. But if you have that, then you position. You have much more structured way of aiming it. So it is in the same sense. If I have two mirrors, I have a much more defined algorithm for making it go at 90 degrees. But if I have just one, it is like keep shooting, and maybe once in a while you can actually get it. So, right?
Sir, you said that you can decrease theta.
Yes.
So, if you decrease theta to 0, then spatial fringes are gone.
Yes.
Then only the temporal, if there is temporal.
There is an effect of time that you can still see. Yes.
Time effect takes place.
Yes.
And
No, not take place, can take place. If I change time, then you can still see the effect of time. But the effect of theta is that it increases or decreases the fringe density. Once theta is at 0 fixed, then I'm not seeing that effect. But I can still change my time and see some interference effect. What is that? That I haven't shown you, which I will, but probably at the end, so that we don't have to align it back.
So now when we are seeing spatial fringes, means that time coherence has to means it is there.
No, anytime you see any fringe, if you
All
see,
the coherence
yes,
patterns
if you
will be
see a fringe pattern, that means whatever are the coherences conditions, all the conditions satisfied.
Is that everything, every type of coherence is
Yes,
satisfied?
yes, yes,
We are
yes.
looking at a particular
You are
one.
looking at the effect of only one or so, yes. But if you see an interference pattern, if you can call something an interference pattern, that means all the coherence conditions are satisfied. Otherwise, you won't see
You
it.
might be observing at one of those.
Yes, 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 yes. If you don't see interference pattern, then you can't conclude the reverse. That you know none of the interference conditions satisfied. It is like could be just one of the interference conditions not satisfied, or two, or maybe all. But if you do see interference pattern, that means you have coherence in all the degrees of freedom. Fine. Okay. So yes.
Here it is the pixel distribution. This is a 2D pixel, like there is a 2D distribution what is showing in upper.
Mhm.
But when it is showing the graph, it is in 623, 650, 700 only one.
Mm-hmm.
So
Yeah. So yeah. You're absolutely correct. So this is a two-dimensional camera pixel, and you see what you're saying is essentially fringe in this side, this direction. There is no fringe in that direction. So you can do fringe in that direction as well. One can do fringe here. I'm coming with a beam, which is like theta x theta for theta x. If I can introduce theta in the y direction, then it will have fringe in this direction. And if I can introduce theta in both, then you will have in a particular direction. You can also have a checker chess kind of thing, the fringe in this and fringe in that. So in that you will have a chess kind of pattern. So all those things can be done, yes. But here this is a simple kind of demonstration. Just a beam, and then you introduce an angle in one direction, and then in that direction you have fringe. If I do it in this, the fringe will be in opposite. And if I do something in between, this fringe which is like this, you just kind of take like that. Okay, so any other question? Yes.
You say if they see the interference pattern, then all the interference constants are satisfied.
Mm-hmm.
Can you just separate it? We are looking at temporal pattern.
Yeah. So then you have to have more knowledge as to what this experiment is doing, which degree of freedom you are addressing, and so on. But if I show you interference pattern and very high visibility, then you don't need to look at any detail. You can just right away conclude that all the coherence conditions are satisfied. But let's say if you don't see interference pattern, then you need to check that how exactly the experiment is being set up, which degree of freedom is being explored, and then you can conclude whether which particular condition is not satisfied. But if you do see it, you don't need to look at anything. It is guaranteed that all the coherence conditions are satisfied. Fine. Any other? Okay, so we'll take a little detour and do some fun thing in the sense of the refinement. Since from next class we're going towards the quantum aspect, and we'll do things more rigorously. But I think the one interpretation you might have heard as interference is that even in this interference setup, now if you think in terms of if you go to quantum and think in terms of photon, this laser which was emitting intensity will now start emitting single photons. So if it emits single photon, then how the interference kind of works out is that the single photon either can go this way or it can go that way to the detector. And if there is no way of telling which way the photon, then you will see interference. But if there is a way of distinguishing it, fringes are gone. That's the interpretation you have heard. That's called the indistinguishability. So indistinguishability you can't really quantify and so on. We have much powerful method of coherence, but we can quantify things. We have much rigorous math. But I just want to show you something of fun, from that perspective. Again, we will not address any coherence aspect, but just how you could introduce indistinguishability, how you could erase that indistinguishability and so on. And very quickly then I'll come back to the temporal coherence aspect to the extent that I can.
Sure.
At this point, let me just try this micrometer, moving it and see what happens. So this is my micrometer and I can move this whole thing back and forth, and this is the that gauge that I can use. So what will happen if I change T1 to that interference pattern? Any guess? What both? No, but what will happen to the pattern? Shift, right? Because we are not changing really theta, but we are doing the delay, that means introducing a phase, and so essentially this maximum will become minimum, minimum will become maximum, and the effect of that will be the whole thing is just going in one direction or the other. So let's try, and hopefully that's how it should be. You see this moving? Okay, go. There's a fluctuation because the stable is not very stable, but I think, yeah, now it is stable. And now again, if I go back, you see the fringe density is not changing. It's just the whole thing is shifting like this. That means I'm not changing theta. So this is also the effect of time, because just the overall phase that we have introduced. Okay, so for the spatial, temporal, I have promised that will come back. So now I just want to do some cool stuff with the polarization. Right. So what we have right now is this laser actually is vertically polarized. So this laser sends out a vertically polarized light. Okay. So this arm goes like here. It is vertically polarized. It is also vertically polarized. So the photon that comes here, if I detect it, I find it vertical. Once I find it is vertical over here, there's no way I can find whether it came this way or that way. It could have come this way or it could have come that way. So there's no way to distinguish them, the two paths, and that's why you are seeing interference. Now the question is, let's say we put a half wave plate here. Everybody knows what a half wave plate is. Half wave plate is people who have done optics lab, they do know what is half wave plate, right? So it turns a vertically polarized light into horizontally polarized light. So now if that is the case, and if I am here, if I detect a photon and find that to be vertical, I know it came this way. If that photon is horizontal, then I know it came this way. So I am able to distinguish them, hence no interference. So let's try that if that happens. 45. Around half a plate. Around 45. So of course the half plate wave plate needs to be at the correct angle, because this is a rotating device, it can actually rotate. So if it's at about 45 degree, then it turns a vertical into a horizontal. Okay, see that fringes are gone, almost gone, right? And that's because we have introduced a half wave plate right over here. And this makes it horizontal, so if I detect a photon here, it could, if I see it here to be vertical, then of course it came this way. If horizontal, then I know it came this way. So the visibility is gone, there's no interference. Now the question is, can we do something to erase this possibility that I am able to distinguish? Huh? Again, that's a very obvious answer, that you do the reverse of it, or there, turn this one also into horizontal. Yeah, that is fine, but something else without using a half wave plate? Huh? No, without use something else, not a half wave plate. Not a retarder, but something else. One more? Where?
Before the laser,
After passing the first one here, what kind of beam splitter? It just splits the beam. Okay? So wait, if it just splits the beam,
That means direction.
yes. No. See, if I just put a beam splitter Let's say if you want to split it this way, then half the beam goes this way and half the beam goes that way. Now if I detect a photon here, find that to be horizontal, I still know it came this way. Find that to be vertical, I still know it came this way, hence there will be no difference. Something else.
Polarizer.
Polarizer, okay? What does that do? So this doesn't work. So you have to put a polarizer here. At what angle?
45 degrees.
At 45. Okay, excellent choice. So with 45, well, if I put a polarizer here at 45, what is the polarization I'm going to see here? 45, right? Once if polarizer is 45, it doesn't matter what comes in from this side, I will see 45. So if I see a 45 degree polarized photon, how do I know which way it came? You cannot, right? Because this V can also give me 45. This H will also give me 45. And their probability or the projection will be exactly the same. So now if I put a polarizer at 45, there's no way I can distinguish, whether the photon came this way or that way. Hence, the interference should be back from that argument. So let's try. I have a polarizer, and this is at about 45. Let's try that. So this is my beam splitter. That's the camera, and that's where I'm actually putting it. And people are happy, but not that happy. I know. So, well, you were just insulting me this moment ago, right? So we have not spent too much money on the polarizer, right? So, but I think one thing you should note is there's a very high visibility fringes, right? It's the fringe pattern, the intensity pattern is a little messy, but the fringe visibility is 100%. Okay, so this indistinguishability, it has come back, but the polarizer, since I again didn't spend too much money on the polarizer, it is not very high quality, so it does change the beam quality, especially intensity profile. But the fact that it does come back, right? In fact, you can see that if I remove the polarizer from here, if I remove the polarizer, the photons are again, or sorry, the two paths are now distinguishable. There's no fringe pattern. But if I now put a polarizer here or here, what happens? Suppose I put a polarizer here at 45. Partial, right? So at least some partial distinguishability I'll have, because, so let's remove this one, and if this is at 45, then this is 45, this is horizontal. So so if I detect a photon, so even this 45, wherever it is, can give a projection, and then I can't really figure out. So there will be some partial fringe visibility, and let's just try if that happens. So I'm putting in it between. Some fringe visibility. Again, I think now my alignment is a little bit off, the overlap and all. But the main central region of this 100% probably is this one, because I think the overlap intensity has gone down too much, and you see the thickness of these points. But this region, if I concentrate at visibility, well, I think I have not convinced you fully on this one, but at least you can believe me on that. Let me not claim too much here, because I don't have a perfect setup. Okay, so this was just a little detour as to what polarization can do, and I will remove the half-wave plate as well. Any question? So we have then shown you the spatial interference. We have also shown you some effect of polarization. The polarization, the indistinguishable argument, this is coming from Feynman and so on. But now we know, I mean, if this is horizontal, this is vertical, you will not have interference, it's orthogonal. So we do know the rigorous math to actually prove it. But that is also a fun way of looking at it, especially when you have the single photon interpretation. Okay, so next what we are going to try, and we are not saying this will succeed, is we'll try to look at some temporal effect here, temporal coherence effect here. So first of all, as I was saying, that if I change this angle, bring it to about 0, then you will see just no interference pattern, just intensity. It comes this way, comes out that way, and those two, of course, they have to add up. So what we have done is this one, you can see, this one is another mirror, and this we are, making such that the beam from here also goes onto this camera. So we will take some time to, yeah, you need to just expand it, right? Then it will come. Okay. Well, this may or may not work. Yeah, if you have a question, yes.
Introducing the polarizer, why make it the fringe pattern so distorted?
Which one?
After introducing the polarizer,
No, in that case, earlier we were doing either we were perfectly distinguishing them, in which you see perfect interference, or perfectly not able to distinguish, in which you see no interference. This condition was supposed to be that you would distinguish only partially. So that's why you had some visibility fringe, neither completely gone, not completely there.
when you put the polarizer just before the detector,
Okay.
at that time the fringe pattern became distorted.
Oh, that distortion was because the polarizer was not very high quality. And that's why he's happy with me that I didn't spend too much money. So it's like a film polarizer. If it has some, surface variation, thickness variation, and since the interference pattern, it will cause, good enough distortion. And again, it doesn't have the transparency, the coefficient of transmissions and all. That's not perfect. But whatever got out, you see the fringe visibility was very high. So that is what I kind of wanted to stress. But yeah, polarizer quality was not very good. So theoretically everything is nice, but yeah, experimentally a lot of issues. If you want better quality, you spend more money. Some people don't like to spend that much money, and then you will have to settle with slightly lower quality. Okay, so now what we have is that we have two beams. Not two beams. This is output number 1, output number 2, and we have put a mirror here, and it comes like that. And that is what this extra mirror is for, if you can see this one. And so from here, it goes like this to the detector, and this one comes like that. So this is port number 1, port number 2, and if you add these two, intensity, integrate and then integrate and then add, this should equal to how much intensity came out from the laser. So now let me try to change theta. You want to change from this or no? Yes. So we'll try to on top. Fantastic. In fact, this doesn't happen. This is so this is port number 1, port number 2, and can you remove the auto scaling? Otherwise, you will not see the property. Just remove the auto scaling. Sometimes if you have smart devices, the devices if they are too smart, then that is a problem. So we will remove its smartness. So then. So smartness is if camera sees too much intensity, it kind of. So now what you see here is that most of the intensity is coming out from this, and some intensity you get from that, and that is the Mach-Zehnder field, right? The intensity as a function of cosine T1 minus T2, cosine tau. So as you increase tau, you can get the condition whether it's minimum or maximum. So if you remember. I as a function of tau, where tau is T2 minus T1, it is a fringe pattern. So for some tau, there is no intensity. But what happens to the intensity? It goes to the other side because the energy has to remain conserved. So if I draw the other thing, okay, this is I1. And then you have I2, and so it will be something like this. So that if you add I1 plus I2, it has to equal to the intensity of the laser. But as a function of tau, this is what the laser, this is what the interferometer does, and that is hopefully what I actually would want to show you. So how do I change tau? I will change tau by introducing a delay in 1 hour, and that's my stage. And when I'm changing it, I'm changing all this to mirror together. So it just goes like this, and that just introduces the delay. So let's just, so what happens? What do you expect now? You have two spots, one bright, one not so bright. And if I introduce tau, then what happens? Huh?
Related brightness.
It kind of right. So let's just try. Hopefully it works. So I'm moving T. This bit. Can you see the sinusoidal pattern? Yes, almost. I mean, seeing that will be very difficult unless I kind of plot it in the sense of time and intensity. But you see this one going on almost nothing, and then kind of switching back and forth. So I mean, eyes cannot really draw, but if you actually drew, you will see the sinusoidal variation in the intensity. And of course, these two add up to the full intensity. But in each arm, if you introduce a tau, you do see a sinusoidal pattern of intensity as a function of tau. And this is all with theta equal to 0. So this is non-trivial. I was not sure if I could do it here, by the way. Thank you. Because this Mach Zehnder on this kind of optical table, but this is not optical table, it's just a regular. So this is actually very good. So this micrometer is actually not very fine. This is also cheap enough. It's not very expensive. Because what is the distance scale that you need to change to see one fringe? That is like lambda. And this helium neon laser is 633 nanometer. And since this is in double pass, so half of that, about 350 nanometers. So I need to move back and forth about 300 nanometer before complete one fringe passes. Of course, I don't have that kind of control. With at least this, we have more sophisticated thing, but we can't bring that over here. But at least you can see the complementarity you can very easily see. The sinusoidal pattern is difficult, and it is not random because if I leave it, it will settle after a while. This is very sensitive actually. You can have this air in this region ever so slightly different refractive index in the air in this case, and that will also change the fringe pattern. Not fringe pattern, that the intensity of the two are. So see that? That will be airflow. So in fact, Mach Zehnder interferometer is used as a very sensitive detector for these things. Not clapping and detecting that, but airflow or putting a phase object and so on. Very, very sensitive. Of course, I don't have that sensitive the micrometer here, but you get the idea that in principle, just the little airflow is able to kind of change the refractive indices of this one with respect to that one ever so slightly. That it changes the phase, relative phase, and thus the interference pattern. Okay. Right. Now at this point, we can still we have seen some temporal effect. We have some time. Now the last thing I want to show. This will be even more difficult. I didn't think I could go up to this point, but now that we have, let's try to see if we can see some effect of temporal coherence. So far, this is very highly coherent because the visibility I was getting, why is the visibility 91%? I think this is focusing somewhere else, that's why. It's in this range, that's why it's so high, but I think this we need to ignore. Oh, we need not ignore, right? That can still be the real spatial fringes. But okay, let's just ignore at this point. So far what we showed you is the very high visibility fringes. That means spatial coherence is very high, temporal coherence is very high. Right now the setup that I have no way of reducing the spatial coherence, but I have a way of reducing the temporal coherence. But let's see if it works. So we will again bring the fringes here so it's easy to see, because fringe visibility we can't see here. That is like you change intensity as a function of tau, they plot it, and then only you can see the visibility. And if I actually did that, which I cannot here, I don't have the equipment, if I actually did that with the intensity of this one as a function of tau, I will see very high quality fringes. And you have seen that this one almost goes dark, right? And then bright. So that is a proof that it's a very high visibility. But we'll come back to these spatial fringes and then increase this tau to the extent that we can, and then we'll see if that decreases the visibility. So that will be proof that if I increase tau, that decreases the temporal coherence. So let's hope that it works. Now first of all, let's get back the fine. So I have these, you're probably looking at that, right? The first one. So we have the fringe pattern, we have the fringe pattern, and visibility very high. Okay. So now you will not see that this one is completely dark. Why? What we will see if you align it properly, that these will be complementary. Then this is bright, this one is dark, and kind of so on. But of course, you have, since there is a spatial fringe, you will have lighting here and lighting there as well. So very high visibility fringes, and maybe now we can concentrate on just one. We don't need to have two, and maybe you can increase the. Do you remember the numbers? Yeah, that's fine. Maybe you can do 600 was better, no? The vertical.
Vertical.
Okay. So very high visibility fringes. That means perfect spatial coherence, perfect temporal coherence. Now what I will try is that push this entire thing back, and so that increases the tau, and hopefully you will see a lower visibility than this. But again, this for that we'll have to kind of stop it, bring it back, and then show you. 90% it won't work. 10% if it works, then we'll actually see it. So do you unscrew and then bring it back? That's very easy. Okay, so let's just unscrew the whole thing. And hopefully the alignment remains healthy. No? Oh, there it is. You can actually see it. Nice. Oh, I didn't expect. Okay. So you see this again, by looking at the two-dimensional, your eyes cannot really make out that contrast. That you'll still see it as kind of dark, but it's not dark. This is a 0, so it is not coming all the way to 0. But this is something else. This is the overall intensity. There's no intensity, hence it is coming down. But that's the overlap region where you see fringes. But the maximum is wherever it is. Minimum is not coming all the way to 0. Hence the visibility is 63%. We know that the spatial coherence is very high. Somebody is asking it. Here we know spatial coherence is very high. That's how I know it is due to temporal coherence. And then they say that this is lower temporal coherence. Now if I continue, so when this mirror was wherever it was, visibility was 100%. Now this entire thing is shifted back to visibility is about 70%. If I continue in this manner, so that it comes down to some 0% or 10%, then I can fit that coherence curve and find the coherence time. Okay, but this you can see the visibility, nothing changes, just this we have increased the tau and the visibility has decreased, and that is the effect of temporal coherence. And this is with the prior information that the coherence, spatial coherence area of this source is really large. So the decrease in visibility is not due to spatial coherence, hence it is due to the temporal coherence. Fine? Question? Yes?
So what is the
Coherence length, I mean, I cannot do it from here. For example, I actually pushed it back 5 centimeters. maybe about 10 centimeters in the double pass. So that was from 100 to about 70. So the coherence length of this laser will be maybe in 10 centimeter range. It's definitely not 100 centimeter. It is definitely not 1 centimeter. So it is in that range, 10 centimeter or something that this particular laser has. Right? So if you have another source, and if the coherence length is micron, then you have to align this very, very accurately, and I will have to have even more expensive stuff there. And if the coherence length is, let's say, meters, for example, I do have a laser in my lab, the coherence length of that is 25 meters. In that case, you don't really care. This is T11, you can go to T10 with this and it will still interfere with perfect visibility. So you can have sources of any coherence length. But yeah, this is actually the way that you push it back, calculate the visibility, few points, fit the curve, and that width of that coherence function, degree of temporal coherence, that is the coherence time. Fine? Any other question? Okay, so we can also continue it afterwards. So this week I tried showing you temporal interference, spatial interference, effect of temporal coherence, and some effect due to polarization. Also effect due to if you introduce the this angle, and what I was not expecting but still showed you is the Mach-Zehnder fringes, and also the effect of temporal coherence. So next Friday, we'll again do similar demonstration. In fact, that day we'll bring more expensive stuff here, a single photon camera. So we'll do the similar spatial fringes, not in this setup, in some other setup, Young's double slit, the classic. And in that Young's double slit experiment, we'll try to generate this interference pattern by recording one photon at a time. And so you'll have a dot structure turning into this nice kind of pattern. So that you'll be kind of convinced that interference happens at the single photon level. So even at the highlight level, interference happens at the single photon level only, and that we have discussed that the classical explanation, although it works at highlight level, but it is fundamentally incorrect, and the quantum is the correct description, which works at any light level, by the way. But yes, you typically use the quantum description only at low light level. So next Friday, not on Wednesday. Next Friday, there's a class tomorrow as well, Saturday. So next class is tomorrow, and then another class, and then on Friday we'll show you that this interference pattern, the actual explanation is at single photon level, and we'll try to generate that interference photon by photon, and then maybe hopefully you'll be convinced that that's how it works. So okay, so thank you. Any question if you have, you can hang around for a while after this. So thank you.